Hello everyone, I Madhuja Kundu from Electrical Engineering Department going to present the topic called Diode Operation and Characteristics, which includes the subtopics named PN junction, formation of depletion region, barrier potential, diode operation, forward bias, reverse bias, voltage current characteristics of a diode, types of diode and applications of diode. Now, understand diode functions such as forward voltage drop, reverse breakdown voltage, and the VI characteristics curve. In circuits, investigate the practical applications of diodes in electronic circuits, including rectification, voltage regulation, signal modulation and demodulation, and overvoltage protection. Evaluate performance. Assess the performance of different diode types in real-world scenarios and their impact on the efficiency and functionality of electronic devices. This project aims to provide a thorough understanding of diode operation and characteristics, enhancing the ability to apply this knowledge in designing and analyzing electronic systems. Now, the starting of the topic from the PN junction. A p-type material consists of silicon atoms and trivalent impurity atoms such as boron. The boron atom adds a hole when it bonds with the silicon atoms. However, since the number of protons and the number of electrons are equal throughout the material, there is no net charge in the material, and so it is neutral. An n-type silicon material consists of silicon atoms and pentavalent impurity atoms such as antimony. As you have seen, an impurity atom releases an electron when it bonds with 4 silicon atoms. Since there is still an equal number of protons and electrons, including the free electrons, throughout the material, there is no net charge in the material, and so it is neutral. If a piece of intrinsic silicon is doped so that one part is n-type and the other part is p-type, a p-n junction forms at the boundary between the two regions and a diode is created. As indicated in the figure, the p region has many holes as majority carriers from the impurity atoms and only a few thermally generated free electrons, which are minority carriers. The n region has many free electrons that are majority carriers from the impurity atoms and only a few thermally generated holes, which are minority carriers. Now we should learn about formation of the depletion region. The free electrons in the n region are randomly moving in all directions at the instant of p-n junction formation. The free electrons near the junction in the n region begin to diffuse across the junction into the p region where they combine with holes near the junction, as shown in the first figure. Then, before the p-n junction is formed, we should recall that there are as many electrons as proton in the n-type material, making the material neutral in terms of net charge. The same is true for the p-type material. So we can conclude that total positive charge equals to total negative charge. When the p-n junction is formed, the n region loses free electrons as they diffuse across the junction. This creates a layer of positive charges, pentavalent ions, which are immobile charges, near the junction of n side. As the electrons move across the junction, the p region loses holes as the electrons and holes combines. This creates a layer of negative charges, trivalent ions, which are immobile charges, near the junction of p side. These two layers of positive and negative charges form the depletion region, as shown in the second figure. The term depletion refers to the fact that the region near the p-n junction is depleted of charge carriers, electrons and holes due to diffusion across the junction. We should keep in mind that the depletion region is formed very quickly and is very thin compared to the n region and p region. After the initial flow of free electrons across the p-n junction, the depletion region has expanded to a point where equilibrium is established and there is no further diffusion of electrons across the junction. The reason behind this is as electrons continue to diffuse across the junction, more and more positive and negative charges are created near the junction as the depletion region is formed. A point is reached where the total negative charge in the depletion region repels any further diffusion of electrons into the p region and the diffusion stops. Same thing happens for holes also. In other words, the depletion region acts as a barrier to the further movement of electrons across the junction. Now, the barrier potential. Anytime there is a positive charge and a negative charge near each other, there is a force acting on the charges as described by Coulomb's law. In the depletion region, there are many positive charges and many negative charges on opposite sides of the p-n junction. The forces between the opposite charges form an electric field as illustrated in the figure by the arrows between the positive and the negative charges. This electric field is a barrier to the free electrons in the n region. That is, external energy must be applied to get the electrons to move across the barrier of the electric field in the depletion region. The barrier potential of a p-n junction depends on several factors, including the type of semiconductive material, the amount of doping, and the temperature. The typical barrier potential is approximately 0.7 volt for silicon and 0.3 volt for germanium at 25 degrees Celsius. Because germanium devices are not widely used, silicon will be used throughout the rest of the lecture. Now we should discuss about energy diagrams of the p-n junction and depletion region. The free electrons in the n region that occupy the upper part of the conduction band in terms of their energy can easily diffuse across the junction and temporarily become free electrons in the lower part of the p region conduction band. After crossing the junction, the electrons quickly lose energy and fall into the holes in the p region valence band as indicated in the figure. As the diffusion continues, the depletion region begins to form and the energy level of the n region conduction band decreases. The decrease in the energy level of the conduction band in the n region is due to the loss of the higher energy electrons that have diffused across the junction to the p region. Soon there are no electrons left in the n region conduction band with enough energy to get across the junction to the p region conduction band, as indicated by the alignment of the top of the n region conduction band and the bottom of the p region conduction band in the figure, which is on the next page. At this point, the junction is at equilibrium and the depletion region is complete because diffusion has ceased. There is an energy gradient across the depletion region which acts as energy hill that an n region electron must climb to get to the p region. Here are the diagrams of flowchart energy diagrams illustrating the formation of p-n junction and depletion region. Now coming to the diode operation. What is a diode? A diode is made from a small piece of semiconductor material, usually silicon, in which half is doped as a p region and half is doped as an n region, with a p-n junction and depletion region in between. Diode symbol. A standard diode symbol is represented as above. Diode construction. Diodes can be made of either of the two semiconductor materials, silicon and germanium. When the anode voltage is more positive than the cathode voltage, the diode is said to be forward biased and it conducts readily with relatively low voltage drop. Likewise, when the cathode voltage is more positive than the anode, the diode is said to be reverse biased. The arrow in the diode symbol represents the direction of conventional current flow when the diode conducts. Now, the forward bias. To bias a diode, we should apply DC voltage across it. Forward bias is a condition that allows current through the p-n junction. The figure shows a DC voltage source connected across a diode to produce forward bias. The effect of forward bias on the depletion region. As more electrons flow into the depletion region, the number of positive ions is reduced. As more holes effectively flow into the depletion region, the outside the p-n junction, number of negative ions is reduced. Reduction in the negative ions due to forward bias. This depletion region is indicated in the figure. Here, equilibrium, no bias is produced, and then in the second diagram, forward bias narrows the depletion region and produces a voltage drop across the p-n junction equal to the barrier potential. Then the effect of the barrier potential during forward bias. We should recall that the electric field between the positive and negative ions in the depletion region on the either side of the junction creates an energy hill that prevents free electrons from diffusing across the junction at equilibrium. This is known as the barrier potential. When forward bias is applied, the free electrons are provided with enough energy from the bias voltage source to overcome the barrier potential and effectively climb the energy hill and cross the depletion region. Now coming to the reverse bias. Reverse bias is the condition that essentially prevents current through the diode. The figure shows a DC voltage source connected across the diode in the direction to produce reverse bias. If we examine the diagram carefully, an illustration of what happens when a diode is reverse biased is shown in the figure, because unlike charges attract, the positive side of the bias voltage source pulls the free electrons, which are the majority carriers in the n region, away from the p-n junction. As the electrons flow toward the positive side of the voltage source, additional positive ions are created. This results in a widening of the depletion region and a depletion of majority carriers. We should also talk about reverse current. Reverse current, the extremely small current that exists in the reverse bias after the transition current dies out, is caused by the minority carriers in the n and p regions that are produced by thermally generated electron hole pairs. The small number of free minority electrons in the p region is pushed toward the p-n junction by the negative bias voltage. The conduction band in the p region is at a higher energy level than the conduction band in the n region. Therefore, the minority electrons easily pass through the depletion region because they require no additional energy. Reverse current is illustrated in the figure. Now, the reverse breakdown. Normally, the reverse current is so small that it can be neglected. However, if the external reverse bias voltage is increased to a value called the breakdown voltage, the reverse current will drastically increase. This phenomenon is known as reverse breakdown. Then the next topic is voltage current characteristic of a diode. When a forward bias voltage is applied across the diode, current flows through the diode. This current is called the forward current and is designated as IF. The resistor is used to limit the forward current to a value that will not overheat the diode and cause damage. With zero voltage across the diode, there is no forward current. As you gradually increase the forward bias voltage, the forward current and the voltage across the diode gradually increase. A portion of the forward bias voltage is dropped across the limiting resistor. As you continue to increase the forward bias voltage, the current continues to increase very rapidly, but the voltage across the diode increases only gradually above 0.7 volt. The diode forward voltage increases to the right along the horizontal axis, and the forward current IF increases upward along the vertical axis, as shown in the figure. VI characteristic for reverse bias. When a reverse bias voltage is applied across a diode, there is only an extremely small reverse current IR through the PN junction with 0 volt across the diode. There is no reverse current. As you gradually increase the reverse bias voltage, there is a very small reverse current and the voltage across the diode increases. When the applied bias voltage is increased to a value where the reverse voltage across the diode VR reaches the breakdown value VBR, the reverse current begins to increase rapidly. Temperature effects. For a reverse bias diode, as temperature is increased, the reverse current increases. Keep in mind that the reverse current below breakdown remains extremely small and can usually be neglected. And for a forward bias diode, as temperature is increased, the forward current increases for a given value of forward voltage. Now, diode current voltage relationship. Shockley diode equation. When a voltage V is applied across a PN junction, the total current I flowing through the junction can be shown to be given by I equals to Is exp EV by eta kBt minus 1, where Is is the reverse saturation current, E is the electronic charge, Kb is the Boltzmann constant, T is the absolute temperature of the junction, and eta is a dimensionless number depending on the semiconductor. For germanium, eta is unity, while for silicon, eta is approximately 2. Now, the diode equivalent models, which shows piecewise linear model, simplified model, and ideal model, and their condition model and characteristics curve. In case of ideal diode, when a voltage is just positive, it will conduct and having zero internal resistance, and in reverse bias, it will block the current completely. In case of practical diode need a cut-in voltage to conduct. Below the cut-in voltage, diode current is very small. Also, the diode have a small resistance when it is in forward bias. Now, we should learn about types of diodes, like PN junction diode, Zener diode, Schottky diode, light-emitting diode, which is and function application. Junction diode current flow induction amplifiers on the Zener operates in reverse bias, is designed to conduct in the breakdown region. Schottky diode has a low forward voltage drop and fast switching speed, and is used in high-speed switching circuits and power rectifiers. LEDs are used in display screen indicators and lighting. Photodiodes are used in light detection in cameras, optical communication systems. Now, the applications of diodes. Application of diodes includes rectification, voltage regulation, signal demodulation, overvoltage protection, and light emission. Rectification is converting AC to DC, used to power supplies to provide a stable DC voltage for electronic devices. Voltage regulation is maintaining a constant voltage level. Zener diodes are used to protect circuits by providing a stable reference voltage. Signal demodulations are extracting information from modulated carrier waves. Diodes are used in radio receivers to demodulate AM and FM signals. Overvoltage protection is protecting circuits from voltage spikes. Light emission converts electrical energy into light. LEDs are widely used for display screen indicators and general purpose lighting. Now, the end of the project. I am really grateful to Dr. Saurabh Chakraborty sir, Assistant Professor, Department of EC, for his valuable guidance and support throughout the completion of this project named as Diode Operation and Characteristics as part of my BTech degree at MAKOUT. I also thank the Electrical Engineering Department at MAKOUT for providing the resources and environment necessary for this project. Special thanks to my peers and family for their encouragement and assistance. In conclusion, the project on diode operation and characteristics has provided a comprehensive understanding of the fundamental principles and practical applications of diode. Through detailed exploration of the diode's operation in both forward and reverse bias condition, we have observed their critical role in various electronic circuits, like operation of diodes, types and application, and importance in electronics. This project has understood the significance of understanding diode characteristics to effectively utilize them in various applications, thereby enhancing the design and functionality of electronic circuits. The knowledge gained through this project will be instrumental in future studies and the practical applications in the field of electronics. Thank you. Hello everyone.